Okay, so we're on page 21 of your packet. So first thing we do with any limit problem, if it's approaching a real number, we just go ahead and insert that whole number. Now, what if I change this problem to a one-sided limit as a plus or a minus? Will that change the process? Same process, right? Doesn't matter if it's a one-sided limit. We're just going to insert that 0, see what happens. Oops, sorry. First step first, 0, 0 in for x. I get √2 minus √2. 0 over 0, that confirms that there's a hole in the graph. The limit does exist. So it doesn't matter if I'm approaching from the left or from the right, it's going to be the same value. Everything will be consistent. There's no need for any decimals, right? So we know there's a special method for these problems. This is the conjugate method. Multiply numerator, denominator by the conjugate, which is the same exact terms as you see here in the numerator. The only thing that you change is the sign between the terms. Don't change all the signs, just the sign in between. All right. Now, the whole point of this process is so that the numerator can clean up and so that we can find a pairing with this x, right? We know that this x is causing the hole in the denominator, or that the 0 in the denominator, and we're trying to find a matching pair that's causing that 0 in the numerator. So we're trying to find a match for that numerator, that denominator. So we're hoping that resolving the radicals can do that for us. Okay, so we fold this out, so distribute through. Distribute through, distribute through. The middle term should drop out nicely. We have the exact same terms. There's just one is positive, the other is negative, so that goes away nicely. And do not expand the denominator. The denominator is ready for you to reduce. We just want to find a way to clean up the numerator. Okay. So continue to reduce. Now, this is what I saw in the quiz, what some students did. I saw some students starting to cancel out before reducing everything in the numerator. In this case, it ends up working out, but we really want to try to you really want to kind of wait to reduce until your entire numerator is cleaned up as much as possible. So 2 minus 2, we can combine those like terms. That gives us 0. So now we're good, right? Now there's only an x remaining, and we can cancel these out. And also, now if this x was attached to something else through multiplication, we can still cancel out. But if it's like x plus 3, x plus 4, we're not able to reduce. But here we can reduce. There's nothing left in the numerator. Let me rewrite it. So we see the cause of the whole, which is the x and x. Remember, there's still a 1 left over in the numerator. Reevaluate 0 in for x. Now, root 2 plus root 2 doesn't equal to 2. Right? Think of it as this. This is 1 root 2 plus 1 root 2. That's equal to 2 root 2. You leave like this, or you can rationalize the denominator either way, but in our course, we don't have to rationalize the denominator.
If we were to rationalize it, would it be root 2 over 4?
Yeah. Okay, any questions, Kwame? Okay, number 2. Says for x equals 4, the function is equal to x squared plus x minus 20. What value should be assigned to make the function continuous? Okay, so anything dealing with continuity, I'm just going to go through continuity conditions because everything is set up for me. I don't have to deviate from continuity conditions. Just whatever I do, continuity conditions, whatever I need to find is stored inside those conditions. So that makes it easy. We don't have to try to be, figure out what we need to do. If we see anything with continuity, let's just step through it. Okay, so here's our function. We know that this problem is focused around x equals 4, so that's our c value. So first condition is order pair. Good point. If I try to find h of 4, I plug in 4, I get 16 plus 4 is 20. 20 minus 20 is 0. 4 minus 4 is 0, so we get 0 over 0, which means that this point is undefined. There is no point there, and we know, okay, 0 over 0 means there's a hole, and that's going to come into play when we do our second condition, but at least we know to begin with, our point is undefined. Second condition, does a limit exist? It should, because we just saw that 0 over 0 show up. But to confirm again, we are getting 0 over 0. Which means that there are some common factors that's hiding in there that we want to identify and remove and find the limit. Multiplies to be negative 20, adds up to be 1.
5 and 4. 5 and negative 4.
Good. Factors match and cancel out. Reevaluate. And we see there's an issue, right? We see that h of 4 does not equal to the limit. And make sure that, I think for this problem,
It asks us to
right, it asks to figure out what to make h of 4 equal to. But I do want to point out this specific step here, that if this is a normal problem and it'll ask you for whether the function is continuous or not, This is what I'm looking for. I don't want to see undefined doesn't equal to 9. I'm looking specifically for this step, right? It's really just taking that third condition. I'm sorry. I need to. Variables match here. Everything should be H. But if you look at your third condition for continuity, right? The only thing you're replacing is the C value, but I am looking for this step, okay? To show that, to show all the specific notation that I'm looking for. But in this case, right, the problem says, what can we make H of 4 so that the function is continuous? So here, because they're not equal to each other, if we make H of 4 9, then we can get that to happen. So if we make H of 4 equal to 9, then we can make that third condition nicely set up and pass all the conditions. Okay. Any questions? Number 3. Given that our function looks like this, find the value for the constant k that will make the function continuous at x equals 0. So we know we're just going to blindly follow our continuity conditions, and before we know it, we should be able to solve for k. We don't do anything special or different because the problem is set up differently or because we're trying to solve for a variable. So what's our p value?
0.
0. Okay, so step through our conditions. C being 0. First step is finding the order pair f of 0. Which one does this go into? First one, we see the equal sign. First condition down, keep going. Second condition is about whether the limit exists. Can we rely on one limit statement or do we need two?
Two.
We need two because we have different functions split on either side of our C value. Which means that in order for us to determine if there's a true limit or not, we have to look at the behavior from both sides of our target. So we'll do limits as x approaches 0 from the left side of 0. And left side of 0, that's less than 0, so that's the x squared minus 2. I'll do that in a second. And then the other side, approaching 0 from the right side of 0.
3x plus k.
Yeah, 3x plus k. Because 0 from the right is greater than 0. Next step, we're going to evaluate each of our one-sided limit. Again, it's always the whole number first, right? We're not going to do any decimals here. The decimals is the notations here is just to help us determine which piecewise to choose and also to show that we are doing one-sided limit. So 0 for x, we get 0 squared minus 2, which is -2. Insert 0 in for x, we get 0 plus k, which is k. Now, we're trying to force continuity here, so what must happen if we want this second condition to pass?
Limit of f of x as x approaches zero from the negative direction must equal limit f of x as x approaches zero from the positive direction.
Good. We need both the one side limits to be in agreement, so that's going to force -2 to equal to k. And as soon as we solve for whatever we're looking for, we can stop, right? We don't have to go any further. It just says find the value for the constant k. And I like the idea of just stepping through the same process every time, and we can find whatever we're looking for just by going through.
So we're allowed to just say k equals -2 and be done.
It's not asking for justification, so just go through your steps. Okay, we're going to omit number 4, number 5. Any questions so far? Yeah. Oh, for this one here.
Yeah, I don't think we had a problem with that.
So we go through conditions, right? So first condition is, does the point exist? Second condition, does the point, does limit exist? And the third condition is, does the point equal to where the limit exists? So those are 3 conditions, right? Continuity conditions. So we're just trying to figure out what is the k value that will allow all 3 conditions to pass. And if we just step through each condition, we should be able to figure out which, what the k value must be to allow each condition to pass. So the first, does the point exist? We know that our c value is 0. So we insert 0 into the first piecewise function, and that gets us -2. Second condition, does a limit exist? We can't rely on one limit statement. Normally, it would be the limit as x approaches c of f of x. But because we have the function split on either side of 0, we have to do approaching c from the left side of c, and also approaching c from the right side of c. And that's the step that we're taking here. So from the left side of 0, we're choosing the x squared minus 2. From the right side of 0, we're testing the 3x plus k. We evaluate them, we get -2 and k. But in order for the true limit to exist, these two have to be in agreement. So we just take the results of these and set them equal to each other. And before we know it, we have the k value that we're looking for. Okay, number 5. Let f be a continuous function. Selected values of f are given in the table. So it says, what is the least number of solutions? Solutions does the equation f of x equals 1/2 have on the closed interval. Sorry, this cut off here. Closed interval 1 to 8. So I think the easiest way to do this is if we just graph this out. I mean, this is basically application of IBT, but if we just graphed all these points and figured out, if we connected all these points together, what's the least number of times that the graph is going to cross through a y value of 1/2?
3.
3. So I think it's easier to see it if we graph it out. So take all these order pairs here. So 1, -2. 2, 3. 3, 1. Five, -5. 8, 7. So let me highlight where this y equals 1/2 is. So y equals 1/2 is right here. So if I connected all the dots, what's the least number of times that the graph has to cross through 1/2? So we can see that between f of 1 and f of 2, the graph is going to cross through 1/2 because we're going from -2 all the way to 3. So that's one time there. Between 2 and 3, we see that if I go from 3 down to 1, I'm not guaranteed to hit 1/2. So there's no intersection there. But then from 3 to 5, from 1 to -5, right? I start off above 1/2. I end up below 1/2. So through that process, I'm going to at least cross through that 1/2 at least a second time, another time. And then from -5 to 7, right? If I'm going to have to connect all these points here, it's going to have to cross through 1/2 at least one more time. Now, it could be more than that because there could be things happening between these points that we don't see. But if we're told that the function is continuous, then it's got to at least hit that y equals 1/2 3 times. Does that make sense? Page 22. Okay, so if we're approaching showing it's kind of being read -3 from the left side of 3. So we're just looking for a one-side limit, so we're just going to pick a point to the left, right? That negative notation means that we're choosing a point to the left of -3. And we're going to head towards -3. So that means we're going to draw an arrow to the right to head towards -3. And where's that arrow headed to? 3. So now that one-side limit just tells us that we're just going to go just in that first, just from that direction from the left. We don't care about what's happening from the other side. It's not asking for the full limit. Even though the full limit does exist, it's only asking for where that arrow is pointing. Over here, approaching -3 from the right side of -3. So now we can pick a point on the right side of -3, head towards -3, and They're in agreement. That's also going to 3. So because of these two statements, we can say the true limit is 3 because, right, if we pick a point on both sides of -3, they're both headed towards the same destination. True limit is 3. Okay, approaching -1 from the left side of -1. So there's actually a graph here. I don't know if you can see it. It's actually on top of the graph here. So if I pick a point on the left side of -1, if I head towards -1, it's taking me to a y value of 1. If I pick a point on the other side of -1, so if I pick a point like 1.2, 1.3, or sorry, -0.9, -0.8, and if I head towards -1, it's taking me to a y value of 2. So these are not in agreement. The true limit is going to be does not exist. In order for a limit to exist, the graph has to approach the same y value from both sides. See a disconnected graph, disconnected branches. Use continuity conditions to justify if the graph is continuous at x equals 1. Determine the type of discontinuity. So we already have an idea. Let's see, at x equals 1. Okay. So go through our continuity conditions, or that's our C value. First step, where's the point f of 1 is down here at -5. Okay, second condition. Does the limit exist? We see that if I pick points on either side of 1, arrows are headed towards the same y value, so I can say that the limit does exist. The limit as x approaches 1 from both sides are both headed towards the same y value, same y value of 1. So first condition passes, second condition passes. The third condition, though, we see that third condition just means we take the first two and we compare them. But I don't want us to just say 1 doesn't equal to -5. I want us to say f of 1 is not equal to the limit as x approaches 1 of f of x. And that is confirmation that if the third condition fails, what type of discontinuity do we have?
Removable.
Removable.
I have a
Specify the
question.
location at x equals 1.
I have a question.
Why for 2 wouldn't limit of f of x equal 2?
Let's see, say that again.
For
The limit is-
condition 2.
Oh, condition 2. Sorry, yes, that should be 2, my bad, thanks. Look at the x value, right, the y value, it's approaching a y value of 2, that should be 2. Hey, was there a question on Teams, or was that what you were gonna say too?
Yeah, that's what I was gonna say.
Okay, sorry about that. Okay, number 7. Find the value of k that makes the function continuous. So I'm just going to step through continuity conditions. Find the point, find the limits. But for number 7, this feels a little bit more confusing to have it this way. So what this x doesn't equal to -3 means is that this function exists to the left of -3 and to the right of -3. So if we want to write it as a previous piecewise function with a less than and greater than, we can do that. And that maybe can make things more straightforward to look at. So I'm going to rewrite this first condition like this, because if it exists everywhere except -3, then that means this function is going to exist to the left of -3. Now the point is over here at -3, but then to the right of -3, it's also contained within this function as well. So if I step through my continuity conditions here, I can write it either way. I'm going to use the bottom one. First condition, does the point exist? We know that our C value is at -3. We ask ourselves what G of -3 is. And G of -3 is just equal to K, so we're just gathering information. We don't know what K is yet, but we're going to keep going.
We're using fx.
Say it again.
We're using fx. Find the value of k that makes fx continuous for all root numbers.
Yeah,
Doesn't matter.
yeah, it doesn't matter. Yeah, and I'm sorry, and on the test, I don't know why there's a different variables here. It should be the same variable. I'll just make it all the same, G. But if you said F, that's fine as well. Okay, second condition, does limit exist? We always ask ourselves, do we need to use 2 limit statements or can we rely on one? Remember, order pair never gets touched by limit, and order pair doesn't have any impact with limit. If we could do 2 one-sided limits, right? One for the left of -3, one for the right of -3. But if we notice, these are the same functions, so we don't have to rely on one-sided limit. We can merge them together and just rely on one limit statement. I mean, we can, but if we do 2 limit statements, we're doing the same problem twice. So we only need to do one-sided limit if both sides are showing different functions. Right? Then we have to look separately to see what the behavior is on both sides of -3. Okay, first things first, insert -3. We get -3 squared, which is 9. 9 minus 3. 6. 6 minus 6, 0. -3 plus 3 is 0, so we get 0 over 0. That tells us there's a hole. There's a real number answer waiting for us. If we just factor and reduce, we can find it. Reduce, reduce, reevaluate. Limit exists, so we keep going. Third condition, what will it take for the third condition to pass?
G of -3 is equal to limit x approaches 3.
So if I want the third condition to pass, my point has to be in agreement with the limit. So in order for that to occur, then I'm going to take these results and set them equal to each other. And when I do that, I automatically am able to solve for k just by going through my conditions.
What would be an example, like not being able to pass something?
If g of -3 was like 9, then if these are 9 agreements, then 9 doesn't equal to -5 and stuff. But this problem is a little bit different. This one is saying, this is kind of leaving it open-ended and it's asking, okay, what will it take for this function to be continuous? And
If you have that K.
right. So we're just inserting, replacing that -5 in for k to allow for everything to work out. Now, if this was like a different value and this was like set in stone, like 9, then we could just say that, right, function not continuous because 9 doesn't, or these two are not in agreement and stuff. But if it's open-ended, we can kind of go backwards and kind of fill that in. Okay, number 8, it says, find, basically just find these two problems separately. Okay, so we're just going to treat them separately. It's just kind of merging two problems into one. So here's number 8. Sorry, thanks. Yeah, again, number 8. These are two separate problems. They're unrelated to each other. We're just going to solve them separately and then look for answer choices. Okay, so first thing we do, right? If it's a real number, we're just gonna insert that whole number value in just to see what we're dealing with, right? We don't know what category we're dealing with yet until we insert 3 in for x. Just 3 though, right? No decimals here. So 3 in for x, we get 3 times 4. So we get 12 over 0. So what does that tell us about what's happening?
There's a vertical asymptote.
Vertical asymptote. Okay. We know that the true limit does not exist, but then we look back at the problem and realize, oh, it's not asking for the true limit. It's only asking for what's happening as we approach that asymptote. And if you can imagine, if you're trying to approach an asymptote, there's only two things that the graph can do, right? It's either going to go up to positive infinity or it's going to go down to negative infinity. And because we're choosing between two options, positive or negative infinity, that's the only reason that we go to decimals, right? We're never going to use the decimal to find some decimal value. We're using decimals to choose between these two options. So if you're down to these two choices, that's the only time you're going to play with decimals. Because we don't know which direction the graph is headed. Is it going up or is it going down? So what's a value that we can test?
3.1.
Yeah, so I can test a value slightly to the right of our target. Insert 3.1 in for x, and we don't really care about the decimal value. We just want to know whether we get a positive or negative, and then from there we can decide if we can choose between these two options. So 3.1 in for x. Okay, so numerator is at a positive or negative value. Positive. 3 minus 3.1 is negative. So therefore, positive over negative is negative.
Negative infinity.
So we know that the graph is going to look more like this. Okay, so here is the second part of 8. Separate problem. Now, how is this different than part A? One is approaching a real number, and the other is approaching infinity. So we have a completely different set of rules for real number versus infinity. With real number, we just plug in the whole number. With infinity, what do?
We're looking to see the degrees match.
See what the relationship is between the highest degrees of the numerator versus denominator. Now, what's preventing us from seeing the true behavior of the numerator?
The numerator is not, it's factored out.
Yeah, it's factored out, which means that if you look at the factored form, it's not giving you a true reading as to the degree of the numerator. So what should we do in the numerator?
Factor it, but we only really need to factor the first values.
Right, so let's expand, right? So let's expand, get rid of the FOIL, expand whatever. We want to get rid of the new, get that numerator cleaned up because right now, it's the true behavior is hiding behind those parentheses. So we're going to compare degrees, but we're not quite ready for it yet. But yeah, I think what you said is good. We don't have to pull everything out. It's just the first term, right? Only the highest degree matters, but you're more than welcome to expand all the way out just to have everything worked out. So if your limit is approaching infinity and you have something that's in factor form, clean everything up, right? Because if I want to compare degrees, I don't want to get a false reading because, right, it's possible that we may look at this and think that the degrees are not matching because the denominator is higher. But here, now that everything is cleaned up, the highest degree in the numerator is 4. The denominator is also 4. That means there is a limit, there is a horizontal asymptote, and what do we look at?
The difference between the coefficients.
Yeah, we just do the ratio, right? Ratio of the coefficients here, so 3/1 is equal to 3. Our limit.
If the denominator degree is like 4, it would still, you just take the coefficient of the numerator.
Yeah, let's talk about the other two scenarios. Okay, so if the degrees match, we take the ratio of the coefficients. Let me do a part C and D here. What if it was limit as x approaches infinity of 2 minus 3x cubed over 4x squared? And still infinity. We're still going to compare degrees, but now what do you notice? Numerator is higher, so what does that mean? That means this value is getting larger and larger, either in the positive or negative direction, because if the numerator is higher than the denominator, that overall fractional value is getting larger and larger. So that means it's either going up to positive infinity or it's going down to negative infinity. And how do we decide between these two signs? Let's test a value in the direction that we're headed. We're headed towards positive infinity. So if I test x equal to 100, I can narrow down between my two choices. So if I plug 100 in for the numerator, 2 minus 3 times 100 cubed, that's going to be a negative. If I insert 100 in for x in the denominator, I get a positive, negative.
I just want to hand you this right now.
Great.
Sorry to interrupt.
Yeah.
Thank you.
And for part D, let me so I've done 2 of the 3 scenarios, right? Degrees match, we take the ratio. If the degree is higher than the denominator, then we know we're choosing between 2 options. We test a value that we're headed in the direction of. And then what if we have this limit as x approaches negative infinity of what about this one? Yes, because if my denominator has a higher degree, then we know that my denominator is growing at a much faster rate. That fraction is getting smaller and smaller and smaller. It's going to be equal to 0. Limit is headed towards 0. So make sure you know the 3 scenarios when you're going towards infinity. Okay, number 9. I'm going to skip number 9 since we've seen that quite a bit already. Let's do number. Oh, sorry. Let's go to the graph here.
Do the other number.
Number 9. Sorry, this number. Okay, so limit as x approaches negative infinity equals negative infinity. What that means is this is telling me that I'm going to follow the arrow as it exits to the left of the graph. And as it exits to the left of the graph, it's going to head down. So I know my graph is going to look something like this as it exits the graph. As it approaches -4 from the left side of -4, approaching 3, I'm sorry, -3. Just need to show that stem coming out from the left side of the hole. Approaching -4 from the right side of -4. So approaching -4 from the other side is going to head towards 1. H of 6 is undefined. Okay, so that just means that I'm not going to fill anything in at 6. It's just going to be an empty space there. Limit as x approaches 0 from the left side of 0 is equal to infinity. So that means there's an asymptote, but I'm only going to show the branch headed towards infinity from the left side of 0. So I'll do this. The limit from the right side of 0, or the limit as x approaches 0 does not exist. So we can do anything that we want on this side. We can have it matching, we can have it nothing at all. But these are basically the same statements. It's just now this one provides just behavior from the left side. Okay, approaching 3 from the right side of 3 is -4. Approaching 4, there's an asymptote. Now, negative infinity means that I want both branches to head towards negative infinity from both sides of 4. Limit as x approaches 6 is equal to 3. So that means I need the graph to extend from both sides of 6. And then finally, as we exit the graph to the right, the graph is going to flatten out at -2. So there is a horizontal asymptote here. So as we approach positive infinity, we want to have the graph to somehow end up leaving the graph along a flat, getting flatter and flatter towards -2.
You have to connect the dot. I should draw a line on both sides.
-4.
What do you mean -4? No, because there's nothing indicated anything to the left between the horizontal. and-
Yeah, it doesn't tell me anything about the behavior on the left side, so I can leave it blank. I mean, I could connect it as well and make it, so there's a lot of options. If you want to add more things to it, you can.
But I thought for like, you probably wouldn't have to have,
Well, there's a hole there.
F of -3.
so you could just leave a hole without a line on it.
Yeah, so for G, it says it just asks for, it just says that the limit as x approaches 3 from the right side of 3 equals -4. It doesn't say that the full limit exists. You can make it exist if you want, but I always like to put a hole there because then I know that there's nothing else that could conflict with that point. But in this case, if you filled it in, it wouldn't conflict anyways. It just feels safer that way. Okay, good luck, guys. Thank you.
Thank you. So is two kind of like this, where you do K equals 4? It kind of like gives you like.
Yeah, it is. It's basically the same thing. It is.
Okay.
I don't really have
So the answer is right here.
Okay, I worked it out. Yeah. So I said each of 4 is undefined.
Okay.
2, the limit exists. Okay,
Okay.
see, and then third condition, see it, third condition, the conditions don't match, so I just redefine each of 4 equals 9, yeah.
So that one, this one says like different. So which one should I do on the test? This one says they're equal, but then you wrote down the date.
Okay, they're yeah, I made that K. Here I said it's technically undefined, so yes, either way is fine. Either way is fine. You can write it this way, but ultimately, I represented that K as something I'm going to solve for later.
Oh, okay.
But here I was just going through it like as if I didn't see that K until the very end.
Okay, and then you said like to make it continuous that point. Okay, I see what you're saying. So,
Same, it's basically the same process as this.
okay, gotcha, thank you.
So for this problem, I don't think am I just looking for Y values? Basically, it's case based.
Exactly. If you find the limit, then you're just filling in that hole with the thing.
So literally what I want is I just plug that value into that, and just get rid of this. So when you, are you testing for both?
Yeah.
So is that why like we get the plus and minus?
But make sure you do Y. Because
Plus minus.
because it's horizontal, you gotta give me the equation.
Yeah, so y equals plus minus 2.
0/6.
And then when we're doing a work, are you gonna take, for example, like for this one, we don't have like a limit?
Yeah, I am looking for proper notation. And make sure you say limits include 3 of f of x. This is actually stating f of x back here.
So when I'm doing my work, I would like this, I would have limit as an x approaches 3.
Speaking of that notation thing, what if you like you just have to did
That's fine. As long as I see it somewhere and that you're carrying it down.
And then for these, like what's I always forget what happens in the third condition. Like how
Third condition is do the first and second condition. Okay, so here it just says find the value of k, so there's no need to go any further. Stop here.
but then if let's
Yeah.
just say it's
If they equal each other, then I would say f of 0 is equal to the limit as x approaches 0 of f of x. So if it's equal, then it passes. If it doesn't equal, then you'll say doesn't equal, and you'll say it's a removable of this kind.
okay. Awesome.
Mhm.
Thank you.
So if it's like just approaching 5, it doesn't say like, it doesn't classify all of those two as right? Do I have to close plug in a number bigger than that?
Just say that there's starting pending, yeah. Yeah, just say limit doesn't exist. Guys, eventually I'm gonna need all your book bags up in the front and then your phones up against the wall.
Right, I see.
I did.
Today's Thursday, yeah.
How many figures do you take?
Yeah, but usually it's like,
A mix?
it's a mix, but it's like a little bit more seniors than juniors, like maybe 60%, 20%.
Okay. Sure.
I remember the first.
We need to. I can see, I'm always.